You were taught the word when you were a child. A top spins, the earth spins, a figure skater spins. And somewhere in school, a teacher told you that deep down inside every atom, the tiniest pieces of you, the electrons, spin too. It's a tidy picture. It's on the posters. It's in the textbooks. And it is wrong. Nothing in this universe is more famous for spinning than the electron, and the electron does not spin. It can't. If it did, if that little ball of charge were really turning to make the magnetism we measure its surface, would have to be moving faster than light. And the universe does not allow that. Stay with me for the next half hour, and I'll show you 3 things. What spin actually is, when nothing is actually spinning. The Motngin Chintram Haimui experiment that caught it years before anyone knew what they were looking at. And the reason this matters more than almost any fact in physics. Spin is the invisible rule that makes your chair solid, that keeps your atoms from collapsing. That is, right now, holding you up off the floor. Receipts on screen, every step. The names, the years, the numbers measured to 13 decimal places. The most precise prediction in the history of science. Don't take my word for any of it. Here's the line we're going to cross tonight, and most channels never do. They tell you everything in the universe spins. I'm going to show you that the most important spin of all isn't a spin at all, and that the difference is the whole secret of why matter exists. Let's start by killing the spinning ball. In the autumn of Motngin Chincham Haimwelam, 2 young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, were staring at a puzzle in the light coming off of atoms. Spectral lines that came in pairs where the theory said there should be one. A two-ness hiding in the data that nobody could explain. And they had an idea so simple it almost sounds like a guess. What if the electron is a tiny ball of charge and it's spinning? A spinning charge is a tiny magnet. A tiny magnet has 2 ends, north and south, 2 orientations. Two-ness. The doubled lines would just be the electron's little magnet pointing 2 different ways. It's a beautiful guess. It fit. They wrote it up. And almost immediately, it ran into a wall built by one of the sharpest minds of the century. Someone did the arithmetic that Goudsmit and Uhlenbeck hadn't, and it was brutal. Let me walk you through it, because this is the moment the spinning ball dies, and you should watch it die with your own eyes. Here's the thing about a spinning object. The amount of spin it has, physicists call it angular momentum, depends on 3 things. How much stuff is spinning, how spread out that stuff is, and how fast the surface is moving. A figure skater spinning slowly with her arms out has the same angular momentum as the same skater spinning fast with her arms tucked in. Spread out and slow, or compact and fast, they can match. Now apply that to the electron. We know exactly how much angular momentum the electron's spin carries. It's a fixed amount, and we'll meet the number in a minute. We know its mass tiny, but known. The only question left is, how big is the electron? And how fast would its surface have to move to make that much spin? So how big is it? Here's where the spinning ball gets its death sentence. We have fired electrons at each other at colossal energies and watched how they bounce, looking for any sign of a surface any size at all. We've found none. As far as every experiment can tell, the electron is a point. Its radius, if it has one, is smaller than 10 to the minus 18 meters. To put that in human terms, that's less than a billionth of a meter. It's smaller, compared to an atom, than a marble compared to the entire Earth, and we still can't find an edge. And now you can feel the trap closing. Squeeze all of that fixed angular momentum into a ball that small, and ask how fast the surface has to whip around to carry it. The answer Lorentz got, and the answer we get today, is the same. The equator of that little ball would have to move many, many times faster than the speed of light. And the speed of light is the universe's one unbreakable wall. We did a whole video on it. Nothing with mass even reaches light speed, let alone laps it several times over. So the spinning ball isn't just unlikely, it's flat out forbidden. The picture on the poster, the little electron twirling on its axis, describes something that cannot exist. Wrong. There's a very human moment buried in this, and I want to give it to you because it's the opposite of the way science usually gets told. It wasn't actually Pauli who first hit the 2 young men with the arithmetic. It was the grand old man of Dutch physics, Hendrik Lorentz. When Goudsmit and Uhlenbeck brought him their idea, Lorentz worked out the surface speed and told them, gently, that a spinning electron would have to turn about 10 times faster than light. Uhlenbeck was horrified. He didn't want to begin his career with a famous blunder, so he ran to their mentor, Pauli Ehrenfest, and begged to pull the paper back before it was printed. It was too late. Ehrenfest had already mailed it. And Ehrenfest told them something that ought to be carved over the door of every physics department. He said they were both young enough that they could afford to do something foolish. Publish, he told them. Be wrong if you have to. So they did. They published an idea whose central picture was impossible, and the idea, minus the picture, turned out to be one of the truest things in physics. The motion was the mistake. The property was the discovery. They were brave enough to be wrong in exactly the right way. So the objection was right to begin with. But here's the twist that makes this one of the great stories in physics. Gaudsmit and Uhlenbeck were also right. The electron really does carry that angular momentum. It really is a tiny magnet. The spectral lines really do split in two. Every measurable consequence of spin is real and sitting in the data. The thing that's wrong is the only part everyone remembers, the spinning. What we just unlocked, the electron carries a real, fixed amount of angular momentum, but it is far too small and far too light to be a ball that's actually turning. The motion was never there. Only the property. So, if it isn't turning, what is it doing? To answer that, I have to take the word spin away from you completely and hand you something stranger in its place. Let's give the classroom its fair hearing first, because the classroom isn't lying to you, it's just stopping one step too early. In the world you can see, angular momentum is exactly what your teacher said. It's the oomph of rotation, a spinning skater, a turning wheel, a planet going round. And it has a wonderful property: it's conserved. It doesn't vanish. When the skater pulls her arms in, she has to speed up, because the spin has nowhere else to go. When a giant cloud of gas collapses into a star, it has to spin faster for the same reason. That's why the competitor video you may have seen is right, that the whole sky is turning galaxies, hurricanes, the water leaving your bathtub. Big things spin because angular momentum is conserved and has to go somewhere. All true, all real. And all of it is the easy half of the story, the half you can watch. Here's the half they leave out. In the quantum world, angular momentum comes in two flavors, and only one of them involves anything moving. The first flavor is the familiar one. An electron can move around the nucleus of an atom, and that motion carries angular momentum. We call it orbital angular momentum, and it behaves more or less the way you'd expect. Something is going somewhere. Fine. The second flavor is the one that breaks your intuition. Every electron, even one sitting perfectly still, not orbiting anything, alone in empty space, still carries a fixed lump of angular momentum. Built in. It came with the electron, like a serial number stamped at the factory. Move the electron, freeze the electron, it doesn't matter. The spin is just there. And I want to be precise about the number, because the precision is the point. The electron's spin angular momentum has a fixed size, and when you measure it along any direction, you always get one of exactly two answers, plus a half or minus a half. In the natural units physicists use, units of the Planck constant, plus a half or minus a half. Never a third, never zero, never anything in between. Two answers, forever. Now sit with how strange that is. If the electron were a real spinning ball pointed in some random direction, and you measured its spin along, say, the vertical, you'd expect a smear of values depending on how tilted the ball happened to be: a lot here, a little there, sometimes nothing. A continuous range. Instead, the universe hands you two values and nothing else. Up or down. As if the question, which way are you spinning, only has two legal answers, no matter how you ask it. That is not how anything that actually spins behaves. That is the fingerprint of something with no classical version at all. And it gets stranger, because the two-ness chases you no matter how you turn the question. Measure an electron's spin along the vertical and get up. Fine. Now turn your measuring device on its side and measure the same electron along the horizontal. You don't get nothing. The way a ball pointed straight up would give you nothing sideways. You get, again, exactly two answers, left or right, 50-50, and the act of asking the sideways question erases the up-down answer you had a moment ago. The electron will not let you know its spin along two directions at once. It only ever has two answers to give, along whatever single line you choose to ask. A real spinning top has a definite axis you could measure from every angle. The electron refuses. It hands you a coin flip, dressed up as a direction, and that is about as far from a spinning ball as a thing can get. So here's the honest reframe, and it's the hinge of the whole night. Spin is not a motion the electron performs. Spin is a property the electron has, like its mass, like its electric charge. You would never ask, how fast is the electron's charge moving? Charge isn't a motion, It's just a number the electron carries that tells you how it pushes and pulls. Spin is the same kind of thing. It's a number the electron carries that tells you how it behaves in a magnetic field and how it shares space with other electrons. It just happens to have units of angular momentum, the units of spinning, even though nothing spins. We even kept the bad word on purpose. Physicists know perfectly well that nothing is rotating. They still say spin, the way we still say the sun rises when it's the ground that's turning. The word is a fossil, a leftover from that beautiful, wrong guess in Matngin Chintram Haimui Lum, and nearly 100 years later, it's still on every poster, still spinning electrons that never moved. What we just unlocked? There are two kinds of angular momentum: orbital, which is real motion, and spin, which is a built-in property no different in kind from mass or charge. Spin always measures as exactly plus or minus a half. Nothing turns. The spinning is in the name only. Now, you should be suspicious right about now. This is a lovely story, but it's the kind of story that's easy to tell and hard to prove. How could anyone ever see a built-in property that involves no motion? You can't film something that isn't moving. So before we go 1 inch further, I owe you the receipt, and it's one of the most beautiful experiments ever performed. It happened in Motngin Chincham Haimui. And here's the kicker. The men who did it had no idea what they'd found. In Motngin Chincham Haimui in Frankfurt, two physicists named Otto Stern and Walther Gerlach built one of the simplest, most consequential machines in the history of the subject. The idea was this: take atoms, turn them into a thin beam, fire that beam through a specially shaped magnetic field, one that's stronger on one side than the other. Then see where the atoms land on a glass plate at the far end. They chose silver atoms, and that choice was clever. A silver atom has just one electron in its outermost shell, all alone, with all the inner electrons paired off and canceling out. So a silver atom, magnetically, behaves like a single naked electron riding through the field. Whatever that lone electron does, the whole atom does, and you can see it. Now, here's what everyone in Motngin Chintram Haimui expected to see, and I mean everyone, because the quantum picture wasn't even fully born yet. If each atom is a little magnet pointing in some random direction, then as the beam goes through the field, each atom gets nudged up or down by an amount that depends on its tilt. Atoms tilted straight up get shoved hard up, straight down hard down, sideways not much, every angle in between. So on the detector plate, you should see a smear, a continuous smudge, a vertical line, fat in the middle, fading at the edges. The bell curve you'd get from billions of magnets pointing every which way. That is the common sense answer. That is what a world full of tiny spinning balls pointed in random directions has to produce. Here is what they actually got. Two spots, two distinct, separated bands of silver, one nudged up, one nudged down, and clean empty glass in between where the smear was supposed to be. The atoms refused to land anywhere except those two places. It was as if you'd lined up 1,000 compass needles pointing in every direction, flicked them through a doorway, and every single one came out pointing either exactly north or exactly south. Nothing else allowed. There's a famous story attached to this. The silver only showed up on the plate because Gerlach was a cigar smoker. The cheap cigars he could afford on a student's salary were full of sulfur, and as he breathed over the plate, the sulfur reacted with the faint film of silver and turned it black, like a photograph developing. They almost didn't see it at all. The beam had split in two. And splitting in two is exactly what you'd predict if the electron's angular momentum can only ever take two values, the plus a half and minus a half we just met. The continuous smear of classical spinning balls never appeared. The quantum tunas did. They had photographed the fingerprint of spin. And now, the part I love most, the part that makes this honest physics instead of a tidy fairy tale. Stern and Gerlach did not know that. They couldn't have. In Motngin Chincham Haimui, electron spin hadn't been invented yet. Gaudsmit and Uhlenbeck were still 3 years away from their napkin. Stern and Gerlach thought they were measuring something else entirely, an orbital effect from the older, half-built quantum theory of the day. They got the right result for the wrong reason. The two spots were real, but the explanation they carried home was wrong, and it took years for the field to circle back and realize what that little machine in Frankfurt had actually caught. I tell you that on purpose, because it's how science actually works, and nobody puts it on a poster. The experiment was ahead of the theory. The truth showed up in the lab before anyone had the words for it. That's not a flaw in the story, that's the most trustworthy thing about it. The silver atoms didn't care what anyone believed. They split into two because that's what the universe does. And they kept splitting into two for everyone who has run that experiment in the 100 years since. And if you want the strangeness turned all the way up, here's what happens when you run that machine more than once in a row. A thing physicists love to do. Take the beam that came out the up, exit. Every atom in it just measured as spin-up, guaranteed. Now send that pure up beam through a second magnet tilted 90 degrees, measuring left versus right instead. Common sense says, these are all up atoms. They have nothing to do with left or right. They should sail straight through. Instead, the beam splits again half left, half right. The machine forced a fresh two-way answer out of atoms that had no business giving one. And here's the part that genuinely unsettles people. Take that left beam now and send it back through the very first kind of magnet, the up-down one. You already measured these atoms as up once. They should still be up. They're not. They come out half up and half down all over again. Asking the sideways question wiped the up-down answer clean. The electron will not hold two of these answers at the same time. It is not a tiny gyroscope with a hidden, definite axis you're slowly uncovering. It's something that only ever has one answer at a time, freshly minted by the question you ask, and a spinning ball simply cannot do that. The machine doesn't read the spin. In a real sense, it creates it. What we just unlocked. In Motngin Chincham Haimui, Stern and Gerlach fired silver atoms through a magnetic field and got exactly two spots, never a smear direct, visible proof that the electron's angular momentum is quantized into two values. They proved spin 3 years before anyone named it. The data led, the idea followed. So the two-ness is real, and it's on a photographic plate from Motngin Chincham Haimui. But there's a second receipt and number, and it's the one that turns this from a good story into the most precisely tested idea humans have ever had. Because spin doesn't just split beams. It makes the electron a magnet of a very particular, very strange strength. And that strength carries a clue the spinning ball could never explain. Let me give you one more number, and then show you why it's the smoking gun. When a charge moves in a loop, it makes a magnet. We've known that since the 1800s, it's how every electromagnet on Earth works. And physics has a clean way to relate how much angular momentum a loop of charge has to how strong a magnet it makes. The conversion factor has a name, the G factor. For ordinary orbital motion, the kind where a charge really is going around in a circle, the G factor is exactly 1. 1 unit of magnetism per unit of angular momentum. Clean, classical, expected. So when people first measured how strong a magnet the electron's spin makes, they expected a 1. If the electron were a little spinning ball of charge, a 1 is what it should give. It gave a 2, twice as magnetic as it has any right to be. For the amount of angular momentum it carries, the electron is exactly twice the magnet a spinning ball would make. And there is no way none to get a 2 out of a classical spinning sphere. You can make the ball heavier, lighter, bigger, smaller. You always get a 1. The 2 is a flat contradiction of the whole spinning ball picture. It was another nail, hammered in from a completely different direction than Lorentz's surface speed problem. The electron isn't just too small and too light to be spinning. It's also twice as magnetic as spinning could ever explain. So where does the 2 come from? In Motngin Chincham Haimui, a famously silent young Englishman named Paul Dirac sat down to do something that had nothing to do with spin. He wanted to write an equation for the electron that obeyed both of the great theories of his time at once, quantum mechanics and Einstein's relativity. The electron is light and it moves fast, so you can't ignore relativity. Dirac wanted one equation that respected both. That's all he was after. And when he finally wrote it down, the equation that now carries his name, something fell out of it that he hadn't put in. The mathematics, all on its own, insisted that the electron must carry exactly the spin Gaudsmit and Uhlenbeck had guessed, the plus a half, minus a half, two-valued angular momentum. He didn't add it. He couldn't have kept it out. The moment you demand that the electron obey relativity and quantum mechanics together, spin appears, unbidden, as a logical necessity. And the equation didn't just predict that spin exists. It predicted its magnetic strength, and the number it spat out was 2, exactly the 2 that had baffled everyone. The 2 that no spinning ball could ever produce came pouring naturally out of an equation about relativity and waves, an equation in which nothing rotates at all. Read that again, because it's the punchline of the entire century-old story. The reason spin makes no sense as a rotation is that it was never a rotation. It's a consequence of the deep structure of space, time, and the quantum, written into the electron at a level beneath motion entirely. Dirac didn't describe a spinning ball. He described what an electron has to be, and spin was simply part of the contract. The wrong picture from Motngin Chincham Haimui had stumbled onto a right answer that wouldn't be properly understood until an equation in Motngin Chincham Haimui Tarm revealed it had nothing to do with spinning in the first place. Now, I told you this was the most precisely tested idea in physics. Here's why. Dirac's equation said G equals exactly 2. But the electron is never truly alone. It's constantly surrounded by a faint, restless fizz of the quantum vacuum particles flickering in and out of existence around it, tugging at it. And those tiny tugs nudge the G factor just slightly off of 2. So the real measured number isn't 2.0, it's a hair more. And here is where humanity did something almost unreasonable. We measured that number, the magnetic strength of a single electron, by trapping one lonely electron in a magnetic bottle and listening to it for months. And we measured it to 13 decimal places. The electron's magnetism is known to about a part in a trillion. Written out, the value of G over 2 is 1.00115965,218, and then more digits still. Then we did the other half. We took the theory quantum electrodynamics, the modern descendant of Dirac's equation, and we calculated what that number should be from pure math, summing up thousands of tiny contributions from the quantum fizz, and the calculation and the measurement agree. They agree to about 12 significant figures. 12. That's like measuring the distance from New York to Los Angeles, call it 4,000 kilometers, about 2,500 miles, and having theory and experiment agree down to the width of a single human hair. Nothing else in all of science is confirmed that well. Not one thing. The most accurate prediction the human species has ever made is a prediction about a property we still, out of habit, call spin, a property of an object that is not spinning, that has no size, and that we have nonetheless pinned down to a part in a trillion. Don't take my word for it. The number is public. The experiments are named. The value is in every particle physics reference on Earth. And I want you to feel what that extra sliver past 2 is. Because it's not a fudge factor, it's a window. That tiny excess, the difference between Dirac's clean 2 and the messier measured number, comes from the electron talking to the emptiness around it. Empty space isn't empty. It's a roiling sea of particles flickering into being and vanishing again, faster than anything can be caught. The electron is forever dressed in a thin coat of this borrowed, momentary stuff, and the coat tugs on its magnetism, nudging the 2 upward by that famous trailing string of digits. So when we measure the electron's magnetism to 13 places, and it matches the theory to 12, we are not just confirming that the electron has spin. We are confirming that our map of the quantum vacuum of literal nothingness is correct to a staggering depth. The misnamed spin turned out to be the cleanest yardstick we have for measuring the structure of empty space itself. What we just unlocked. A real spinning ball must give a G factor of 1. The electron gives 2 impossible for rotation. But exactly what Dirac's Motngin Chintram Haimui Tarm equation predicts the moment you combine relativity and quantum mechanics. And we've since confirmed that number to about 12 digits, the most precise agreement of theory and experiment ever achieved. So spin is real, spin is measured, spin is the most precisely understood property in physics, and spin is not a spin, which leaves the only question that actually matters to you, sitting there in your chair. Who cares? If nothing's rotating and it's all just an abstract property of point particles, why should it change how you see the world? Here's why. Because that 2-valued, motionless, misnamed property is the single reason you are not, at this exact moment, falling through the floor. Push your hand down on the nearest hard surface. The desk. Your knee. Push. It pushes back. It won't let your hand through. And you've probably been told, at some point, that this is because atoms are mostly empty space, but the electrons repel each other. That's the common answer. It's also, mostly, wrong, and spin is the real reason. Let me show you why electric repulsion can't be the whole story. Yes, electrons carry negative charge, and like charges, push apart. But that push is finite. If electric repulsion were the only thing stopping atoms from merging, you could squeeze matter down much, much further than you can. The actual stiffness of solid matter, the reason a table is a table and not a puddle, the reason you can't compress a rock into a marble with your hands, is far stronger than electric repulsion alone can account for. Something else is holding the atoms apart. Something with no force, no charge, no push at all. It's spin. Here's the rule, and it is one of the deepest rules in all of nature. It's called the Pauli exclusion principle, yes. The same Pauli and Pauli won the Nobel Prize for it. The rule is this: no two electrons can ever be in exactly the same state at the same time. Same place, same motion, same everything forbidden. Not, they repel. Forbidden. The universe simply does not allow two electrons to occupy the same quantum state. Full stop. And now watch how spin sneaks in, because this is the connection nobody tells you. Why electrons, and not, say, particles of light? Why do electrons refuse to share, while photons happily pile on top of each other by the billions, which is exactly why a laser works? The answer is spin. There's a theorem Pauli proved the deep version of it in Magnetism Chintrum Born Mui that ties a particle's spin directly to whether it's a sharer or a loner. Particles with half-integer spin a half, like the electron, are loners. They obey exclusion. They refuse to share a state. Particles with whole number spin like the photon, which has spin 1, are sharers. They pile up without limit. That one fact that the electron's spin is a half and not a whole number divides the entire universe into two kinds of stuff. The half-spin particles, the loners, are the stuff matter is made of: electrons, protons, neutrons. We call them fermions. The whole-spin particles, the sharers, are the stuff forces are made of: photons of light. We call them bosons. And which bucket you fall into is decided entirely by your spin, that motionless, misnamed property we've been chasing all night. So follow the chain, because it ends at you. The electron has spin 1/2. Because it's 1/2, the electron is a loner, it obeys exclusion. Because electrons can't share states, when you push two atoms together, their electrons can't merge into the same space. They're forced to stack into higher and higher energy states instead, and that costs enormous energy, and that energy is what shoves back against your hand. The stiffness of the desk, the solidity of the floor, the simple fact that your body has a shape and doesn't collapse into a point, all of it is the exclusion principle, and the exclusion principle is a direct consequence of the electron's spin being 1/2. The same rule builds the periodic table. Why don't all the electrons in an atom just collapse into the lowest, cosiest orbit? Because they can't share. Two electrons, opposite spins, fill the first shell and then it's full, and the next electron is forced outward into the next shell, and the next, and the next. That stacking, forced by spin, is why different atoms have different numbers of outer electrons, and that's why they bond differently, and that's why chemistry exists. And that's why there's such a thing as carbon and oxygen and the particular chemistry of you. Every atom heavier than helium has the shape it has because electrons refuse to share a state, because their spin is a half. And it goes all the way up to the sky. We did a whole video on black holes on stars that run out of fuel and collapse. What stops most dying stars from collapsing forever? Spin, the exclusion principle. The electrons, refusing to share states, push back hard enough to hold up a white dwarf, a whole dead star, the mass of the sun, held off of total collapse by nothing but the stubborn refusal of electrons to occupy the same quantum state. When even that isn't enough, neutrons take over the same job. The same rule that holds your hand off the desk holds dead stars off of oblivion. It is the same fact at both ends of the universe. And if all of that still feels abstract, atoms and dead stars, let me put spin somewhere you may have already been. Inside a hospital MRI machine. Because an MRI doesn't image your body with electron spin, it images you with the spin of the protons inside you, and the proton, it turns out, has spin 1/2 too. Your body is mostly water, and water is full of hydrogen, and the heart of every hydrogen atom is a single proton, each one a tiny magnet with that same two-valued spin. Slide into an MRI, and a huge magnetic field gently lines those proton spins up, like a stadium of compass needles all nudged the same way. Then the machine taps them with a radio pulse, knocks them out of line, and listens as they tip back, each one singing out a faint radio note. The machine maps where those notes come from, and that map is the picture of your insides. A doctor reads it to find a tumor, a tear, a clot. So this property that has no motion, that no ball could carry, that took the smartest people of the Motngin Chintrum Hai Mai's years to even name, we now use it, every day, to look inside living people without a single cut. You may have trusted your life to spin already, lying still inside a magnet, while a misnamed nothing that turns drew a portrait of your own brain. What we just unlocked. Because the electron spin is 1/2, electrons are loners that can't share a quantum state, and that refusal, not electric repulsion, is what makes matter solid, builds the periodic table, makes chemistry possible, and holds up dead stars. A property with no motion is the scaffolding of everything you can touch. So let's put the whole thing back together. Because once you see it, the word spin never sounds the same again. The electron does not spin. The word is a fossil, a beautiful mistake from Mutngin Chincham Haimwe Lum. And now you know exactly why it's wrong, too small, too light, too magnetic, and it gives an answer no rotation could ever give. But here's what's true. The electron carries a built-in, two-valued lump of angular momentum, as much a part of what it is as its mass and its charge. We caught that two-ness on a glass plate in Mutngin Chincham Haimwe Hai, 3 years before anyone had the word for it. We watched it make the electron exactly twice the magnet rotation allows. We pulled it, unbidden, out of an equation that merged relativity with the quantum in Mutngin Chincham Haimwe Tarm. And we have measured the magnetism it produces to about 12 decimal places, the most precise agreement between human theory and physical reality ever achieved. And then, having understood it, we found out that this motionless, misnamed property is doing the most important job in the universe. It is the reason matter takes up space. It is the reason your atoms stack into shells, the reason the periodic table has the shape it has, the reason there's chemistry, the reason there's you. Right now, the only thing standing between your body and a single structureless point is the fact that your electrons have spin 1/2 and refuse to share a room. So the competitor's poster was half right. The universe is full of turning things, planets, hurricanes, galaxies, the water down your drain. But the most important spin of all, the one that makes the solid world solid, isn't a spin at all. It's a property so deep it lives beneath motion itself. Just never change the name. That's the beauty of physics. Not the tidy poster, not the spinning ball you were handed in school. The stranger, truer thing underneath, caught on a plate in Mutngin Chincham Haimwe Hai, written down in Mutngin Chincham Haimwe Tarm, measured to a part in a trillion, and holding you up off the floor at this very second. There is no spin, there is only the property, and it is the reason you are solid. So let me ask you something, and there's no wrong answer. Before tonight, when you heard the word spin, what did you actually picture? A little ball twirling? A planet on its axis? Sit with the image you've carried since school and notice how it just quietly came apart. Tell me in the comments, now that nothing's spinning, what's one word you'd use instead of spin? Just one word. I read every reply, and I genuinely want to see what lands for you. If this gave you a new way to see the solid world, if nothing actually spins, rearrange something in your head, subscribe to the Physics Storyteller. No paywall, no hype, just physics with the receipts on screen, every single time. And next time on the Physics Storyteller, we go after another thing that feels obvious and isn't: mirrors. Raise your right hand in front of one and your reflection raises its left. So why does a mirror flip left and right, but never up and down? The answer is not what you think. Until then, press your hand on the desk and feel the spin holding you up.